Alright, hello. Here is a video that will describe numerical methods to solve differential equations in MATLAB. And this method will actually have you develop your own numerical method. So here I have the heading, I have the what the file is called, the description, my name, and today's date is the 31st. And then I start my codes again with the three main CLC, clear all, close all. Alright, so the first one we're going to do is solve first order differential equations. So dy dt is equal to 3y. So it's just some example. So let's first identify some givens. So first we're going to say t, big T, which is the total time. So we're going to start at 0 seconds, and we're going to go to that 1 second. We're going to increment by 0.01 second. And then why don't we generate our time matrix? So 0 by dt to big T. Time matrix. Alright, now let's do our initial condition, and I'm going to call it y underscore 1 is equal to 50, okay, meters or whatever your initial condition is. Okay, and I'm going to call something y2, and it's going to be the same thing. What I'm going to do is there's two ways to solve this differential equation, and I'm going to show you both ways. Alright, so we have our givens. Now we're going to use this loop to get the solution of that differential equation. So do for n is equal to 1 to t over dt. Alright, so we're doing a for loop, so we got to know how many times we're going to do the for loop. If we divide our total time divided by time step, then they'll give us the number of times that we're going to go from 0 by dt to 1 second. Okay, so here, this part, we're not going to use a function file. Alright, we're not going to make one. We're just going to solve it. And so what we're going to do first is say dy underscore dt 1 is equal to 3 times y underscore 1 of n. Okay, so we just put the differential equation in. So it's dy dt basically is equal to 3y. Alright, and we're using case 1. And then the solution would be y underscore 1 n plus 1 is equal to dt times dy dt 1 plus y underscore 1 of n. Alright, so this method that I just have right here in line 34 is called the for difference method. So we take our dy dt, we multiply it by dt. So now we're kind of left in this section with just the change in y, and we add that to our previous y value. So if we we know our dt and we calculate our dy dt in the previous line, which is line 33, okay, now we have a small change in y and we add it to our original y value, then we can solve for our second y. Alright, excuse me. So that's not using a function file. So now let's use a function file. I'm going to enter down here a few. So dy dt underscore 2 is dy dt function of t of n comma y2 of n. So this time we're going to generate a function file called dy underscore dt fun and put in the differential equation in that function. Alright, so let's do that right now. So go to File, New, Function. Alright, so our outputs can be dy underscore dt 2, and this is called dy dt fun, and let's delete the inputs, which are going to be t and y. So we basically wrote this section in our previous code, previous main script, and so we got to use those in our inputs. We don't have to use them all, but we have to use whatever you need. So dy dt underscore 2, which is our output, is 3 times y. Alright, I'm going to save this. Let's go to desktop. I'm just going to save it on the desktop. And let's go back to our main code, make sure we save that in the same place that our function file is. So I'll save it on the desktop. Yep. Okay, so now what we did is we took the function and we built the function with our differential equation. And so now all we have to do is similar to line 34, y underscore 2 with n plus 1 is equal to dt times dy dt underscore 2 plus y underscore 2 of a. Alright, so there's two methods in order to make your own code. You don't have to use a function file, or you can use a function file. So let's end it. Let's plot t y underscore 1, and let's make it plus signs in magenta. And let's hold on and plot the other one, which is going to give you the same result. And label it. Oops, what happened here? There we go. Time, seconds, and y label is y meters. And the title is Solution to the Differential Equation dy dt is equal to 3y. Alright, now let's go ahead and run this and make sure it works for you. Okay, we'll change directory. And alright, so this is good. We have the magenta right, but our second function is not correct. So let me look to see why. Oh, that's why. If you go back to line 27, that should be 1. Because that's our initial condition. There we go. Sorry about that. So there you go. So this method is solving first order differential equations, and there's two ways you can do it. You can do it inside your loop without any function file, or you can make a function file and do that. Now the reason why I wanted to show you the function file is because it's a little easier sometimes if your function's complicated, and since we're doing the for difference method, this way is probably easier when you don't do a function file. Now there's other methods that they use to solve differential equations. Instead of the for difference method, it's backwards difference method, central difference method, or you'll notice in this when you do second order, It's more accurate what they call Runge-Kutta numerical method. So I'm going to show you that here. Okay, so let's clear all. And we're going to solve second order differential equations. Okay, and we're going to solve d squared theta divided by dt squared plus g over L times theta equal to 0. So let's define our constants. So g is 9.81 meters per second squared. Acceleration due to gravity. L is equal to 1. Oops. That's meters. So length of the pendulum. I'm going to move some lines down. T is 10 seconds. So total time. dt 0.01. And this is our time step. How many we're incrementing from 0. Okay. By dt to big T. This is our time matrix. Alright, here's our initial conditions. Theta of 1 is pi divided by 4. And it's radians. Initial for theta. And then omega, or theta dot, is -1 radians per second. That's our initial condition for omega. Okay. Alright, so go down a few. Okay, so use this loop to get the solution for theta. Okay, so for n is equal to 1 to big T over dt, again, just like we had before. And since it's a second order, alright, you have to basically break that up into two first order and solve them simultaneously. So let's first find theta. So dh dt is equal to omega n. Okay, so that's our first equation. And theta is basically dt, just like we had in our first order differential equation, dt plus theta of n. Alright, we're doing a forward difference method. Now let's find omega, or w. So dw dt is equal to negative g over L times theta of n. And omega is n plus 1 equal to dt times d omega underscore dt plus omega n. End. And now let's plot the solution. So figure 2, subplot 2, 1, 1, plot t versus theta. And let's make this plus signs b, and let's do another subplot. And let's plot t versus omega, and let's make that diamonds that are red. Okay, now let's run this and see if this is going to work. There's our first figure for first order. And here's our, perfect, good. So I didn't label it yet, I will, but the first subplot is theta versus time, and down here is omega versus time. Now you can't tell in this, but let me change the time. But let's first label these. So X label, the X is time, seconds, and the Y label would be theta. So In MATLAB, if you write the backslash and write theta, it'll actually do a theta for you. So I'm going to copy these, paste them down here, change this to omega, and it will give you omega. So that's radians per second. So let's change the time step to 0.1, and let's make it go 20. And let's run it again. You will notice that the solution starts exploding, meaning it doesn't look right. So look at this. So we have theta, omega versus time. And it looks okay, and then all of a sudden at 20 seconds it just explodes. And we know that's not correct. And this is one of the drawbacks when you start doing forward difference method. This simple, we multiply your dt times your d theta dt, so the dt's cancel. You're left with a small change in theta. You add it to theta. And so you could really make it really small time step, so your change in theta is okay. However, that will take a lot of computational time and it's not very effective. So there's another way we do this. And we're going to build a function file, and instead of doing the forward difference, we're going to do the Runge-Kutta fourth order method, which is a very stable numerical method. So let me show you this. So what we're going to do is I'm going to delete all this. And we're going to use this loop for a more accurate solution. And it's called the Runge-Kutta fourth order method. Alright, so what I'm going to do is I'm going to make it a little easier. I'm going to call the solution theta 1 and omega 1. So I'm going to combine our initial conditions into one matrix, and here's the loop for n is equal to 1 to t over dt, and we write k1, and we build our function diff run tt fun of t of n, and let's put our inputs, solution of n, and then we're going to have k2, we'll have k3, and we'll have k4. So that's why it's fourth order, and I'll explain that in a second. So I'm going to copy these lines, paste them in here, but for 2, what we need to do is, to the solution, is we add dt divided by 2, and we multiply it by k1. For case 3, we add dt over 2, but we multiply it by k2. And the last case is we don't divide by dt over 2, we just multiply it by k3. Alright, and we'll end. Before the end, this is how we make our new solution. And I'll explain this again. Sure I got it correctly. K1 plus 2K2 plus 2K3 plus K4. Okay, and then we'll make the function here in a second. Oh, that should be a comma. Okay, so what we do is we first, let's make our solution into one matrix that combines theta and omega. Theta is going to be your first row, omega is going to be your second row, and it's going to be marched in time. So we have our initial value, we're going to calculate our basically time of 0, and then since we're using dt at 0.1, we're going to calculate the new theta at 0.1, and then 0.2, and 0.3, all the way up to 20 seconds of your total time. And this method, this Runge-Kutta fourth order, basically sends 4 different types of solutions, or 4 different values to your function file, which will contain your differential equation, and kind of does an average, or a running numerical method average that helps stabilize your solution. And that's what these values over here do. All right. Basically, you're solving for your next solution, so your next theta and omega, using your previous values, and you're combining these values that we sent to that function file. And then theta becomes your solution, your first row, and then omega is your second row. So let's save that. Let's go ahead and make a new function. Okay, so our new function output will be d solution underscore dt. Our function name is diff run kutt function, and this is t comma solution. And let's put our stuff in here. I'm going to relabel our G and our L. You can use global variables, but I'm just going to leave this. Now theta is our solution is 1, and omega is solution 2. It's the second part of the solution matrix, and theta is your first part. And we can write that first part of the solution matrix. And this is the second part of the solution matrix. Now remember, in a function file, in your main script, when you send in your inputs, which are your t and solution, in your function, it only sends it as one number. So that's why we don't have to write comma, colon, and these values here. Alright, so now let's write our first differential equation. d theta dt is equal to omega. First equation for the first order differential equation, and then d omega dt is equal to negative g over L times theta, and this is our second equation for the first order diff equation. Because when we have a second order, okay, we have to break it up into two first order and then solve them simultaneously. And then let's write our output. So d solution dt is equal to d theta, dt semicolon dw dt. Okay, put both equations into one matrix. Okay, so this is our derivative. All right, and then solve at the same time. So let's save this on the desktop. All right, so now we built the function file, and here's our derivative. Okay, and basically, if we go back to our main function, all right, these K1, K2, K3, K4 are basically our derivatives. We kind of take a better than average of our derivatives. So K1 sends in the previous value for solution and your original time. K2 does your original time, but then sends in this solution plus dt over 2 divided by K1 and gives you a different value. Same thing for 3 and 4, and then we do this numerical combination, and we add it to our previous solution, and we can get a better approximate new solution. Okay, the details on how this happens, if you're curious, I can pull out the papers and show you, but this is a more stable method than doing the forward difference. Alright, let's see if we run this, it will work. So it's working. There's our first figure for the first order, and should be coming up. Here's our second order. Look at that. So this looks right, 20 seconds. All right, the amplitude should be very constant, and it should start at -1 for omega and pi over 4. So there you go. So I would highly recommend doing the fourth order Ranjakutta method. It's a lot more stable than the simple forward difference, but it's a little more complicated to understand, but it should work. All right, I hope this helps. Thanks.